today we'll very much focus on the power. We'll focus very much on the power. Okay. Because again, like I say, one of the performance metrics when you evaluate a system. Okay. So you have a signal. You pass through this a system. So one of the very important performance metrics is the power. So more specifically, we look at the power spectral density. Okay. So the power spectral density is like how the power distributed. Okay, how the power distributed. So it's quite easy to understand. If let's say our communications channel is using some frequency, we want all the power, if possible, to be centralized around that particular frequency. Okay, so now I'm talking to you in this frequency. So that's why, of course, all my power that I use to talk should be concentrated on this frequency, so that you get the signal very clearly. Okay, yeah. If you imagine if my voice, the signal that I use, let's say my voice is such a way that I can spread the power in all frequency, and you can listen to one frequency only, then you will hear the quality will not be good. Okay, so that is a very simple explanation on communication system. So that's why we look at the power spectrum density. Okay, so how we do that? If you know Fourier series, okay, or Fourier transform. So we have one signal in T time domains, and then we change to frequency domain. You see, it suddenly got so many frequency, right? Am I right? You study that? Okay, yeah. So that's why basically we can represent a random process with a collection of signals. Okay, so the spectral characteristic of the signals determine the spectral characteristic of the random process. Okay, so again, this related a little bit with time domains, frequency domains. So that's why you study signal and system before. Okay, you know that the signal in time domains, when you transform into the equivalence frequency domains, you will see that the signal will spread at a range of frequency, right? Okay, yeah. So yeah. So that's why we can look like this. Okay. So yeah. And then if we look at the time from time domains, okay, so if the signal are slowly varying, that means the signal will change slowly, okay, so we say that the random process contains mostly low frequency, okay, yeah, and then that's why the power will mostly focus on the low frequency, okay. Similarly, if the signal varies very fast, okay, so mostly are high frequency, so the power mostly at the high frequency side. Okay, yeah, is that right? Okay, so again, the distribution of power, we call the power spectral density or the power spectrums, and then this is the symbols. Okay, so that's why later we are trying to relate this power spectral density with the statistical parameters. So that's why that's everything that we study. Okay, so we have the power, we have the random processes. And then we know the statistical parameters, the means, the autocorrelations or cross correlations. Okay, so now we want to look at the power spectrum. Okay, so all these are related. So that's why today we focus mostly on the power. Okay, yeah. So according to this Wheeler-Khinchin's theorems, so yeah, I don't remember this theorem also, but I just remember this one. Okay, so what is important is say that, okay, so the power spectral density is the Fourier transform of the autocorrelation functions. Very easy. Okay, so that's why you have autocorrelation functions. If you want to look at the power spectral density, so the autocorrelation function is in time domain. Am I right? Yeah. So that's why if you want to look at the power spectrum, you need to convert the time domain to frequency domains. What is the transform that we use? Fourier transform. Okay, so when you Fourier transform the autocorrelation functions, you get the power spectrum. So that is why the statistical parameter is important. Okay, it's not just explain about what is the average, what is the standard deviation, and so on. It's also tell us what is the power spectrum. Okay, so we kind of like understand the random process even better. Okay, yeah. So for cyclostationary random process, okay, for cyclostationary random process, we look at the Fourier transform of the average, okay, of the average of the autocorrelation functions. So yeah, so that's the slightly difference between these two. Okay, so we look at the examples. So again, so I think after you look at the example many times, you will notice that we always deal with that few examples, right? That few function or that few random processes. So that's why sometimes you have to refer back to the previous examples to see what are the particulars. So for this random process, I think we see a lot already. I think in the previous example, we already calculated the autocorrelation functions. Okay, so this we have calculated in the previous examples. So that's why now if you want to look at the power spectra, we just need to perform a Fourier transform. Okay, yeah. So I think I just added this one. Okay, so this is from the Fourier transform table. So that's why I don't provide the whole table. You can search the Fourier transform table everywhere. Okay, it's also in the textbook. So if you see a cos functions, when you perform a Fourier transform, actually you get two impulse functions or two direct functions that I draw just now. Okay, so you can see that, and then the amplitude will be by reduced by half. So that's why it's half here and half here. Okay, so yeah, if you multiply this, a squared over 2 is just a constant. So that's why you will get this power spectra. Okay, so if you plot the power spectra, is one way. You know, when you look at here, of course, this is a very simple function. You will know how the power spectra look like already. Okay, otherwise you can always plot the power spectra. Okay, that's why you need to know the functions quite well. So this is a direct functions, okay, or it's an impulse function. So this is how we represent these functions. Okay, so can you tell me this part of the function? This one, okay, this signal, is it this one or this one? The right one or the left one for this one?
Right one.
Right one, okay? Yeah, so yeah, we have to make this equal to 0, so f equal to f naught, so that's why it's here, okay? So this part of the signal is here. This part of the signal is here, okay? Yeah, but you see, and no difference that they are the same, yeah. In this case, they are the same. Okay, but in some cases they may not be the same. So you must know how to draw the power spectra. Okay, this is how we draw the power spectra. So what is the conclusions that we have from here? What is the conclusions? You look at here, what is the conclusion? You look at this graph. You can see that the power spectra only appear at two frequencies, f0 and negative f0. Okay, and at all other frequency, there's no power, there's zero power. Okay, so that's how we look, how we interpret the power spectrum. Okay, yeah. So next, okay, so this is another question. Also, I think this is even easier. Again, this function, this random process. So we already calculated. This is the what we call the autocorrelation functions. Okay, and then we just need to perform the Fourier transform. So this is the answer. Okay, so again, I put the note. This is all the Fourier transform you can get from the Fourier transform table. Okay, yeah. Okay, we have another examples. Also, we have done before at the cyclostationary part. So this function we have proven to be cyclostationary, and we have obtained the what we call the autocorrelation functions. Okay, like this. So based on these theorems, for cyclostationary, the power spectra is the Fourier transform of the average. So that's why we have to obtain the average for these autocorrelation functions. So how? So this is the autocorrelation functions, this is the average. Can you understand how? From this part to this part? Because it's a linear combination, right? So we can find the average of this part and then the average of this part. Okay, the average of a cost function, what do we get? The average of a cost functions. That means you evaluate the average over one period of time for sinusoid. What do you get? You always get 0, right? Upper half and then lower half. You always get 0. So that's why the average for this is always 0. The average for this part is a constant. Am I right? Because tau is t1 minus t2. It's just the difference between the time. So that's why there's no time here basically. It's just a constant. So that is why the average of a constant is the constant. So that's how we get the average for this part. Okay, so and then the average for this part is 0. Because the average of a cost function is always 0. So that's how you get this. Okay, so yeah, then you perform Fourier transform. Okay, a Fourier transform for this one. Okay, so here, this is slightly challenging. Okay, so you can see this involves two parts, two functions. So again, if you check the Fourier transform table, if you want to transform two functions that is multiplied, so the frequency domain, the transform is the convolutions. Am I right? So that's why. And then the Fourier transform for 2 you can take out is just half. So for Rx, the Fourier transform of the autocorrelation is the power spectra. So that's why this part is the power spectra of X. And the Fourier transform for cost function is 2 directs, 2 impulse functions. So that's why from here you need to do the convolution of XX, this one, SXF, with this one and this one. Okay, so how do you do convolutions? You have a functions. So yeah, this is your SX. So basically you are doing SS convolution with this one. So you need to perform this. Okay? So that's why because it's a linear function, so what we need to do, we just need to do this. So you need to do these convolutions. How you do convolutions? You remember? We have to plot the two graphs and then we need to move and multiply them together and add together at different frequency. But this is very easy, okay? Because you can see this one is just an impulse function at F0. So this one is just an impulse function at negative F0. Am I right? Yeah. So that's why at all other part is all 0. So it's rather easy to do the convolutions. So at the end you get this one. Okay? And remember these impulse functions, the magnitude is 1. In this case it's half lah, but you can take out the half because it's just a constant. Okay? So for this one, the magnitude is 1. Okay? It's 1. The magnitude is 1 here. So basically it's just 1 multiplied with the SX, and this only happened at this frequency. Right? So that's how you get this one. F plus F0 and SX. The other one, you get this one. So here got half, here got half. That is how you get 1/4. Okay? So yeah, again, you need to do some revisions on Fourier transform. Okay? How to perform different operations. So that is how you obtain this power spectra. Okay. So again, how do we interpret this power spectra? How do we interpret this power spectra? Okay. So very much you can see it's the same. We have the power spectra for X, SX. Okay. When we multiply this random process with a cost function, basically when it comes to the power, you can see that we split the power of SX into two parts. One part at this frequency, plus F0, and other at negative F0. Okay? So that's why you can compare this case with the previous case. It's very much the same. Okay? You can see that the power kind of like split into two parts. One is the positive frequency, another one is the negative frequency. Okay? Yeah. Yeah, because this one is just a cost function and then it's a constant, so you can see the value split into half. For this case, you can see it's the function SX itself. Okay, so if let's say the power spectra SX is a shape, for example, it's a triangle function. Okay, so this is initially the SX is at 0. So we will move this into negative F0 and F0, and the amplitude will reduce by half. Okay, so this is what happens when you multiply a random process with a cost function. Okay, so we have seen two examples here. Okay, so if you want to calculate the total power of the signals, so it makes sense, right? In frequency, all the power they spread at different frequency. So that is the power spectra. If you want to calculate the total power, what you do? You add them together. Okay, so that's where you do the integration of the power, or you do the integrations of the power spectra density over all frequency. So that's why the integration will be from negative infinity to infinity. Okay, yeah. And certainly yesterday I also told, how do I explain negative frequency? So what is a negative frequency? We go back to physics. What is frequency? What is frequency? 1 over time. What does it mean? What does it mean, 1 over time? So that's why nobody asked me what is the negative frequency, or why. I think during signal and system, right? You know the negative frequency. Have you asked Dr. Anis or Dr. Aisha what is the negative frequency? Nobody can. So what is the negative frequency? You study physics, it says, I think it says form 3 or form 1, right? Frequency. Or maybe in primary school you study frequency already. Do you study frequency in primary school? Yes, I think primary school science. No, I studied in kindergarten actually. So only high school you study frequency. So what is frequency? It's the number of cycles per second, right? So 1 over t. So, but what does it mean by negative? What is negative frequency? Go and find yourself. Okay, yeah. Okay, so continue here. If you want to find the power contents, okay, the power, you do integrations of the power spectra density over all frequency. Okay, yeah. Okay, we come back to the equations just now. We know that the power spectra density is the Fourier transform of the autocorrelation functions. Okay, how do we find autocorrelation functions for power spectra? Inverse Fourier transform, right? You know Fourier transform we can inverse, right? Okay, so yeah, so that's why we can obtain the what we call the autocorrelation functions by applying an inverse Fourier transform to the power spectra. Okay, yeah. And if you perform, if you look at the equation for inverse Fourier transform, it's like this. It's exactly like this. Okay, so this is the equation for inverse Fourier transform. Okay, so this is the equation for inverse Fourier transform. Okay, yeah. So that's why from here you see here, if you substitute tau equal to 0, exponential 0 will give you 1. So that's why your equation here will become like this. Okay? Yeah. So when you substitute your tau or your t equal to 0, so that is Rx0. What does it mean by tau equal to 0? That is the T1 and T2 are the same, right? T1 minus T2 equal to 0. So T1 equal to T2. That is how you get this one. So when you do this, you compare these two equations, they are the same. Okay? So that's why yeah, you can also calculate the power, okay, from from the autocorrelation functions by substitute T1, T2 equal to the same number. Okay? Or you substitute tau equal to 0. That is how you get this. Okay? So that's why this equation is very useful for you to calculate the power. You can calculate from the power spectra density, or you can calculate from the autocorrelation functions. Okay? Yeah. Okay, next. We look at the power spectra when we have a random process that passes through the LTI system. Okay? I think yesterday we talked a little bit on the random process passed through the LTI system. We got this set of equations. Am I right? Yesterday? Okay? So we have this set of equations. So when we pass through this, what happened to the power spectra? Okay, so what happened to the power spectra? So we look at here. Again, this is the equations for Fourier transform. Okay, so this is the equation for Fourier transform. Okay, so again, if we substitute t equal to 0, we have these integrations. Okay, we have these integrations, which is equal to h0. Okay, and you can see this part of the integration is here. So that's why my is just mx multiplied by h0. Okay, yeah. This is the standard Fourier transform equations. Okay, so we just substitute t equal to 0. So that is how, f equal to 0, the frequency equal to 0. That's how we get this equation. Substitute into here. That is how we get this one. Okay, so that's why from here we can kind of like understand the my or the relationship between my and mx better. Okay, so that's why you have a x random process. You pass through a LTI system. Okay, so the output y, okay, the means of my is just mx multiplied by the transfer functions or the response of the LTI system at 0 frequency. Okay, what does it mean by 0 frequency? 0 frequency is DC value. Yeah, we studied that in CA, right? Okay, so that's why the means of the random process of the output is just the means of the random process input, the input random process multiplied with the system response, the LTI system response at 0 frequency, okay, or DC value. So easier to calculate, okay. And then we look at the what we call the power spectra. Okay, so we try to relate the power spectra of the output and the power spectra of the input random process. So again, if we perform some manipulations, so the Fourier transform of the negative t is the conjugate. Okay, so again, this is just operations that we can obtain from the Fourier transform table. So if we manipulate this part, we can see that the sy is just equal to sx multiplied with the amplitude of the response squared. Okay, so that is how the sx and the sy are related. So from here we can see that basically the output power spectra and the input power spectra will have the same frequency distributions. Okay, or the powers distribution across frequency, but it's multiplied by this factor. Okay, because this will give you a constant value, right? Magnitude squared. Okay, yeah. So that's why, yeah, only the magnitude will affect the output power. Okay, but the distributions, the power spectral density is very much the same. So that's why it's just the amplitude will change. Okay, yeah. So that is what happens when you have a random process pass through a LTI system. Okay, so that's why when we come to analysis, we assume the signal is LTI. The modeling, the analysis, everything will be much simpler. Okay, very simple to do. So yeah, and then we define what is called cross spectral density. So we have cross correlation. Of course, we have cross spectral density. Okay, so again, it's the same equations. It's just the Fourier transform. Okay, so it's just the Fourier transform. Okay, but we can do a little bit of manipulations here. Okay, so again, it's from here sxy. So if we do the Fourier transform of this one, we get this one. Okay, and we know that rxy tau is equal to ryx negative tau. Okay, yeah. Okay, right, this one? Yeah. So rxy, t1, t2, if we call this Rxy tau, so Rxy T2, T1, remember the first one is for x, the second one is for this one. So this one is this one. So definitely this is equal to Rxy negative tau. Right? Okay? Yeah. So yeah, that's how we have this one. If we put everything into these equations, okay, we can get the autocorrelation, the cross spectral density, okay? So the cross spectral density will be just equal to the spectral density of the input multiplied with the frequency response, okay, of the system, okay, HF. Yeah. So that's why everything is summarized in this diagram. Okay, everything is summarized in this diagram. So that's why if you in your support sheet, if you don't want to write all the equation, you can just draw this diagram. So that's why I say being smart to decide what to put in your support sheet. So yeah. So that's why in time domains like this, in frequency domains from Sx, from the power spectra of the input, how you calculate the power spectra of the output, you just multiply with this one. Okay, you will get this. How you calculate the cross spectra, you multiply with this one or this one. Okay, and you can see here the cross spectra again is different. This is Sxy, this is Syx. Okay, so it's different. So these examples only show how to use all these equations. Okay, it's just how to use all these equations. So again, we have the same random process. Okay, in this case, it's passed through a differentiator. Again, if you check the Fourier transform tables, okay, a differentiator, if you transform, you will get J2 pi f. So that is why HF is equal to J2 pi f. Okay, yeah. You know how to look at Fourier transform table, right? Yeah, okay. So that's why. And from the previous examples, we have this power spectra for X. Okay, I think we just calculated just now. So that's why you can calculate Sy, Sxy. Okay, I'll give you 30 seconds, look at the step. Any questions? Okay, here I should, because it's just the math, I should remove the J. Okay, I should remove the J here. Because if not, you think J squared will give you negative 1. Okay, but we are looking for the magnitude. Okay, so that's why even I put a J there, it's not wrong. Okay, but yeah, I removed it to be better. Okay. No problems, the steps are rather straightforward. Again, this is another example. This is even simpler examples. This random function, random process, and again is the same LTI. Yeah, that is how you get. Okay, next. We look at power spectra in the sum system. That means in the sum processes. So that means when we have two processes, we add together. Okay, two or more processes, we add them together. So what will happen to the power spectra? Okay, so that's why again we assume this set is x plus y. Okay, so when x, y are okay, so it's even simpler. Yeah, we want to give even simpler examples. X, y are jointly stationary random processes. Okay, yeah. So if x, y are jointly stationary, if we add them together, Z will be stationary as well. Okay, I think we tell this in some of the previous lecture. Okay, So that is where we have this Rz equal to Rx, Ry, and then the cross correlations. Okay? I think this one I proved yesterday, right? Okay? Yeah, I think yesterday is Rx tau Ry tau plus Rxy tau plus Rxy negative tau. Still remember yesterday I proved this? Now I just change this to Ryx tau because this negative tau, right? So if you change to negative tau, you get this. Okay? So that's how you get that equations. Okay? So after that, we just need to take the Fourier transform for this one to get the power spectra for this one. Alright? So you do the power spectra, you do the Fourier transform for this, you get this, this, you get this, this, you get this, this, you get this. Okay? Yeah. And then we know that this is a conjugate of this. Just now we already mentioned, okay? Sx, xyx is the conjugate of x, sxy. Okay, yeah. And then we look at this one, okay? If you look at this part, it's something like, you know, a plus jb plus a minus jb, right? So this is the conjugate, right? You can see that the complex part will cancel each other. That is how you get 2 times real. Okay? So this is the general equations. Okay, this is the general equations. So provided if x, y are uncorrelated, if they are uncorrelated, so that's why your Rxy will be mx, my. Okay, yeah, you can replace the Rxy with mx, my if uncorrelated. Okay. If any of this value, that means if any of this process has 0 means, if any of this value is 0, your Rxy will be 0. When your Rxy is 0, the Fourier transform of 0 will get 0, right? So that's why you only have this part. Okay? If, okay? So otherwise you have to use these equations. If any of the mean is 0, you will simplify into this part. Rather easy, rather straightforward. Okay? Yeah. So that's why again from here we see that, you know, if you have z equal to x plus y, the power spectra of z is not just x plus the power spectra of x plus the power spectra of y. If you think like that, it's wrong. Okay? You only have this if only either one, you know, at least one of the process, okay, have 0 means. If the mean is not 0, you will not have this equation, you will have these equations. Okay? Why? Because there is a cross correlation between the 2 processes. Okay? Although it's just x plus y, but they are correlations. So when you look at the power spectra, you have to look at the correlation as well. So that is where we have this part. But if any one of these or both, they have 0 means, then the power spectra will be more straightforward. Okay? Yeah. So yeah, again, we look at these questions, and we also see this question before, okay, where the z is equal to this random process plus the differentiator of the random process, okay, yeah. So yeah, we just call this part as y, okay, call this part as y, and then again, look back to the examples, we have proved that sxy is equal to this. I just copied this from the previous examples. Yeah. And if you look at the real value of this one, you can see this is a complex function because this is a j. I should put the j here. That is very obvious. Okay. So yeah, this whole part is a complex part. That means this function there's no real part. So that's why the real part is equal to 0. So that is where xz is just xx plus xy. So yeah, you just add together. Okay, so this is just mathematics manipulations. it's good also you try to label those examples, because you have the same example at different parts. You try to link it together, okay? So they are all connected. So some of the answer is from the previous part. Okay, I still have a lot. Let me finish Gaussians. Okay, so again, Gaussian process is always our focus because we see a lot of Gaussian process in real life. Okay, so yeah, so yeah, but especially some types of Gaussian process is especially important for us. Okay, and it's easier to do the analysis as well. Okay, yeah. So this is the definitions. So a random process xt is a Gaussian process. If for all times, for all times, the random variable that we generate at different times, okay, they have a jointly Gaussian density functions. That means okay, we have xt, and we know that the t can take different value. For example, t1, t2, t3. Am I right? Yeah, they can take different values. Okay, so they are different. That's why if all this, okay, they have a joint Gaussian density function. That means let's say if I take this and this, they are jointly Gaussians. Remember the equation for jointly Gaussians? They have the autocorrelations coefficients role in the equations. Okay, so if we take any of these, they are jointly Gaussians. So this is a Gaussian process. Okay, or previously, if we confirm this is a Gaussian process, if we take any of this value, any of these random variables, okay, we can write the equation for jointly PDF easily, just using the equations. Okay, so you can refer back to the jointly distributed Gaussian, jointly Gaussian distributed. Okay, yeah. So that is a Gaussian process. Okay, yeah. So I hope you still remember these equations. Okay, so these are the PDF functions of a Gaussian process. So look at these questions. If xt is a zero means, and then furthermore it's stationary, okay, Gaussian random process, and then the power spectra is given as this. This is a rectangle function, okay. So this is a rectangle function. Yeah. So that's why I quickly plot a rectangle function for you. It looks like this. So this is the rectangle functions. So we want to determine the PDF of random variables x3. That means t equal to 3. Okay. So at t equal to 3, actually I updated the lecture notes. I already posted in Spectrum. If you go to Spectrum, there's an updated chapter 3. So I already updated everything. Okay? Yeah. So, yeah, we need to determine the PDF functions of the x3. That means t equal to 3. Okay. So you can see this is a zero means functions. That means xt, for any value of t, the means will be 0. So that's why dx3 is also equal to 0. Okay? Yeah. Next, what we need is, we need to calculate the variance, because to put into these equations, because if we want to find the PDF of the Gaussian functions or Gaussian random process, we need the means, we need the standard deviations or the variance. So we already calculate the means. We can substitute m equal to 0 here. We still have to find the variance. How to find the variance? So we find the variance using the standard equations. The variance is just the value of x3. Okay? So equal to, so yeah, if you remember, variance copyright. So this is the equation for variance. Okay? So that's why you have to find EX squared, you have to find EX. EX is the means, okay? EX is the means. So, and we know that the mean is 0, so this is 0. So that's why we have to find EX, X, okay? And the X is 3. So what is this? This is a autocorrelation. Okay? So this is an autocorrelation. So how to calculate autocorrelations? We don't have autocorrelations, we have power spectra. So we calculate autocorrelation from power spectra. Okay? Yeah. So if you refer back to one of the equations that we have just now, Rx0 is equal to this. So that's why we have to integrate this for all frequency. Okay? And can you integrate a rectangle functions? Very easy, right? It's just area under the graph. So it's just 1000 times 1. So that's why this is 1000. Okay? So 1000 multiplied by 5, so it's 5000. So that is your variance. Okay? Yeah.
What is the one after 5?
What is the one after 5? Where is it? The door.
The door.
This one. This is a rectangle functions. This is the symbol for rectangle function. Then I already plot here. What? Does it look like a rectangle?
What is a triangle?
When there is a triangle, you do triangle functions? Yeah. It's good. You ask me later, you repeat these questions, okay? SSF is 5 triangle F over 1000. Yeah, you do lah, okay? Yeah, I think 1 year this is the exam question or test question. Yeah. If you don't ask, maybe I will give us a test question. You ask already, so this is not. Okay? Yeah. I can give you any function for power spectra. So you better know all the functions. Okay? Another function that's very common is the signal function. Not the sign function, the sign, S-I-N-C. Okay? Yeah. You will see a lot of those functions later. Okay? Yeah. So that's why when we integrate the power, we can calculate the variance basically. Okay? Based on these equations. So if you have variance, you have means, you can find the PDF of the Gaussian process. Okay? Yeah. So slightly different, right? So far we have the random process. We know what is the means, what is the variance. We calculate, you know, autocorrelations, and today we calculate power. How if we have power, how do we obtain the statistical parameters? So that's what we do. Okay, so okay, so I think I will stop here. Okay, yeah. So it continues next week.